Hello, can you hear me?
Yes,
Yeah.
hello.
Yeah, hello everyone. Welcome to this workshop sponsored by Artificial Intelligence and Data Analytics Lab here in Prince Sultan University. And the workshop is presented by Dr. Aman and his team member Salil Batra. And I will give a brief introduction about Dr. Aman. Dr. Aman is Director of Research and Innovation in the Engineering Professional University in India and also in Delhi Atlantico Standra in Spain. Uh, Dr. Aman will give us a brief and beginner introductory about the resource management in fog computing environment, IoT. Welcome, Dr. Aman and Dr. Salil Batra, and the floor is yours. Welcome.
Thank you, Aisha,
Mm.
for giving us this opportunity to share our knowledge with you guys. Hello, everyone. I hope all are doing great. Am I audible?
Yes, yes,
Everybody
doctor, we can
please
hear
come.
you.
Yeah. Okay. Great. So, what about Dr. Saba and other people? Would they joining like later or like?
No, now they
Shall
are
we start
joining.
or wait?
Yeah, they will join in. No.
Okay. So, can we start with the presentation or like what?
Yes, you can start and they will join now in a minute. Okay.
Perfect. All right, dear colleagues, myself is Dr. Aman. I'm leading the ERIC group, which is Engineering and Research Innovation Group. I am the head and director there. This group is founded and sponsored by multiple academic universities and technology industries from Europe, North America, and other continents. So here we have the centers situated in Spain, USA, Mexico, Angola, and now we'll be starting in India as well. So here our prime objective is, to build some strong industry collaborations for advancing the research, for creating a skilled workshop to solve the industry problems. So this is our basic idea. And I met Professor Saba, and then we decided to have some series of workshops to help master students, doctorate faculties to pursue their research based on the current research problems in IoT, cloud, fog, and multiple researches. So this is the resource management in fog computing environment, where we have the phase one, which is the basic training, which is presented by Team ERIC and in association with Artificial Intelligence and Data Analytics Lab, PSU, Saudi Arabia. Next slide, Salim. Yeah, so a brief detail about ERIC. Like as I told you, ERIC stands for Engineering Research and Innovation Group, which is founded by different academic universities across the globe, from Europe, North America, and so on. And we are doing strong industry research collaborations to different universities across the world to create a skilled workshop. The disciplines we are covering is computer science and engineering, information technology, biomedical, advanced sciences, physics, chemistry, maths, and biology, the roles of computers and mathematical modelings in advanced sciences. And then we have different research areas on which we are working on, like artificial intelligence, blockchain technology, fog, IoT, and cloud computing. We also cover wireless communication, 5G, 6G, cyber security, and computational science. Computational science, where we are using computational intelligence techniques for medical diagnosis, for mathematical modelings, and so on. Yeah, so the brief detail is like our team is like it is led by me, and then we have two team heads, Daniel and Rafal, and then we have different team leads and members, which are around 30 plus. So, for example, when I told you about the research disciplines, like for example, fog computing is led by Salil Batra, artificial intelligence is led by somebody else. So we have different members who is leading every discipline. And then we have different international research collaborations with universities in US, Canada, UK, France, and so on. So for today, this was just a basic idea what ERIC is, what we do, what are the different research areas we are working on, and what are the different collaborations we have with universities around the world. So we have just mentioned few universities here. Our total collaboration is more than 20, 30 plus universities around the globe. And for today's workshop plan, we have divided this workshop based on two phases. Like we had a detailed discussion with Professor Saba, and she helped us to plan it very well. in different phases, like we divided it into phase 1 and then phase 2. So phase 1 is today's October 30th, and then we have the advanced training, which is on 13th of November. We could have easily started with the advanced one as well, but to give you the basic ideas, the theoretical concepts, and how different concepts actually work in the frameworks is important to know. So on 30th, we are starting with the basic training. After covering all the theoretical aspects today, after 2 weeks, we'll go with the advanced training, which will give you very interesting insights into the implementation part. Yeah. Next. So in the phase 1 today, which is the basic training content, we are covering different things like introduction to fog computing. What is basically fog actually is, how is it different from cloud, and what are the different research challenges we have in this domain, the resource management approaches in fog computing. Then we have the summary of various approaches to resolve these resource management issues. And very important thing for all of you, if some master students have joined or their guides, or who are guiding doctorates, who are guiding master or PhD students, we also have some research advice for you on the research management approaches in fog, IoT, and cloud. So this will help you in finding the scope of work for your master and PhD students. So you can take these advices. There are different latest problems we have figured out, and then you can throw these problems to your students, and they can come up with different, developing different solutions. We also discuss about the open issues and main challenges of resource management in fog computing. Like, it will give you an idea for last 5 to 10 years what is exactly happening in these areas, how this research is moving, what are the different current research work going on, and how you can be relevant to different good journals or publications as well. Yeah. And then after 2 weeks in the advanced training, we will have the practical overview of different, we have different, like for cloud, we have cloud sim, for fog, we have fog sim. We have different toolkits to implement our ideas, hypotheses, and simulations. So this is a toolkit which is, doing the modeling and simulation of research management techniques in Internet of Things, edge, and fog environment. So we'll teach you everything from scratch to advanced, like how we install it, what are the different steps included in iFoxin, and then we'll provide you the details of fundamental classes of iFox, what are the packages, libraries, including methods, classes, which are important to carrying out the research. And then we'll also discuss and demonstrate you some case studies. We'll execute some live implementations, and you will see different cases, how it works with different case studies related to focusing environment. And then at the end, we'll also provide you the insights of iFoxin geographical user interface for building network topologies, which is also very important part of the research. Yeah. So the basic introduction related to fog computing. Salil, can you please, I will hand over to you now. Please explain them the concepts very well, and then we'll collectively solve their queries, whatever they will have.
Thank you, Aman sir. I'm going to resume with the fog computing concepts.
Full screen?
Yeah. Am I audible, sir?
Yeah, please go ahead.
Okay. So I suppose process the data instantly. Definitely, fog layer cannot replace the cloud tier. Not possible. But still, some of the operations that were required to be, earlier we were doing on cloud, now we can shift them to the fog tier as well. So when we are shifting to the fog tier, we are incurring less latency. Moreover, the energy consumption requirements will be less, because when we move to the cloud also, the data centers are taking a lot of energy. And with green computing is also very trending nowadays because of that energy requirements only. So this is the architecture view. Now the thing is, at the bottom tier, we have the sensors and the smart interconnected IoT devices. Then they are connected through the fog ways. And then why we are doing it? We are reducing the execution time and the bandwidth. And later on, we have the high-end servers and the data centers at the cloud layer. Am I audible? Sorry. Hello? Hello?
Yes, sir. Yes, we can hear you.
Okay. Now, I would like to mention the difference between cloud and fog more based on various parameters like the architecture point of view. Cloud is centralized and fog is decentralized or distributed, you can say. A communication with the devices, as I already mentioned, this distance parameter, this is from a distance, and fog, it is directly from the edge, or you can say the point where the source of data is there. Data processing, it will be far from the source of information, whereas in fog, it will be closer to the source of information. This is true. Cloud is having very large configuration, high configuration. So the computing capabilities will be higher on cloud, and that will be lower on fog. But still, if we can do mini calculations at fog, why to waste our time to go to cloud? Talking about the number of nodes, very few in terms of cloud, but in fog you have a very large number of nodes which are interconnected to each other. Analysis time, it will be long term, whereas in fog it will be very short term and instant decisions will be given. I can take one example of a smart healthcare system where we have a patient monitoring system enabled, and for that patient monitoring we need instant responses because we want to take care about the patient, and constantly the IoT devices are sending the data, and we want the fast processing of that data, so that processing or that analysis time is shorter. Latency will be higher in case of cloud, in case of fog it will be low. Connectivity via internet, or it may require some protocols and standards of fog computing environment. Security will be lower because we are not processing the data locally, whereas in case of fog it will be on higher side because we have a control of the data as we are working on the edges or quickly. Now the next question comes. We have cloud computing, yes, it is used, trending nowadays, but when to use the fog computing? Now, some discussions I have already done. This is just the overview of that or the summary of that. So you will use this fog computing paradigm when you want to send only the selected data to the cloud. I don't want to send everything because IoT devices are generating data in milliseconds, in nanoseconds, and maybe that nanosecond data is not required to be sent to the cloud. So we will filter out the data in the fog layer itself, because fog layer itself can process it, it can channelize it what we want to send to the cloud, so that selected data will be sent. It is used when the data should be analyzed within a fraction of seconds. Yes, this is the major requirement where the latency should be low. Moreover, it will be used when large number of services need to be provided over a large area at different geographical locations. When I say this, I'm talking about the distributed computing. Devices that are subjected to rigorous computation. When I say rigorous computation, it means they require intense computations and processing. We can go with the fog computing. Now, some examples I can figure out here, like car-to-car consortium, devices with sensors, or industrial IoT, which is the need of the hour. So these are various applications. Even smart grids also nowadays. Smart grids are there. Such type of applications. And healthcare is the major area of concern. So there we can go with. Now, in conclusion, what are the advantages of fog computing? It will reduce the amount of data first that is required to be sent to the cloud. Moreover, the distance to be traveled by the data will be reduced for sure because we have the edge layer and the fog layer in between to handle the processing. Apart from that, it will also reduce the overall response time. It will also improve the security as well as the privacy because the data is going to be processed locally. So these are various advantages of fog computing. So we have advantages, but if something is coming with advantage, it is also coming with some demerits, with some limitations. So what are those limitations? As I already mentioned, fog nodes are not that much capable as cloud data centers or cloud servers are. So they are capacity constrained in terms of processing and storage capabilities. It means they can do some processing, they can do some storage for a temporary period of time or just to filter out the data. But if you want really that, okay, it can work like cloud, not possible. Now, furthermore, we have so many fog nodes. They can also go through some energy consumption problem. The reason is we have different variety of fog nodes available. They are not similar. They are not homogeneous. They are heterogeneous. And it will be very troublesome for us to find a suitable fog node for a particular IoT service. And in the process of this, we are taking a lot of energy. We are consuming a lot of energy. Hence, the efficient resource allocation will be effective. Moreover, they are highly variable and they are highly unpredictable type of environments. Because again, they are not centralized, they are not at the same location, they are decentralized, they are distributed. Maybe they have different computational powers. Let's suppose I'm having one N1, N2, N3, N4, N5, and so on. These are my fog nodes, and every fog node is having a different configuration altogether. Maintaining a consistent environment into this will be a very tricky challenge for us. It will be tricky to handle this because they have their different configurations. Moreover, as I already told, the four nodes are large in numbers, so they are difficult to manage sometimes. Not only this, we have some case studies like smart healthcare systems where we can have maximum load because in the COVID time also are addressing something that we need to manage. So these are some points to ponder. And from these points, we are up to the topic of today, that is resource management, because it is all about finding the suitable fog node for the IoT service we are looking for. And until unless we are not able to manage the resources well, all these points will become a great problem for us. So we need to manage them. So how to manage them? The answer is you go with resource management approaches in fog computing. How to do that? There are 6 approaches which are there to highlight: application placement, resource scheduling, task offloading, load balancing, resource allocation, and resource provisioning. Now, all these 6 resource management approaches could be 6 different problems that our research scholars can take into consideration. Every particular resource management approach is a different problem altogether. It's a different issue altogether. And how we can solve it? This is what we are going to discuss. Or what they can offer, what they can add into the research, that will be their novel contributions. So, to discuss, I will be discussing what they are, what are the various types of them, and the next part is till date what state of the art is saying, and I will also provide a research advice or a research guide to those students or those scholars who are working in this area. So let's start one by one with the application placement. I want to pause for a bit of seconds. Just want to ask audiences at the same pace. Are you able to understand where we are right now?
Yes, great. Please continue. Sure.
Okay. So starting with the this is the taxonomy. I will come to application placement. So this is just a taxonomy which is there for all the approaches, and these are various types or categories available under every resource management approach. Such like in application placement, we have centralized, decentralized, and hierarchical approaches. Scheduling could be done statically, dynamically, or hybrid way. Offloading could be done in single or multiple way. Load balancing, centralized, decentralized, and hybrid. Resource allocation, auction based or optimization based. Or resource provisioning, reactive, proactive, and hybrid. So let's go one by one. Now, what is application placement? To understand this term, firstly, broadly, I will say I'm talking about here IoT application. Now, that IoT application could be any. It could be smart grid, smart vehicle system, smart industry or industrial IoT, smart city environment. It could be anything, or smart grids. Let's take the example of smart healthcare system. So this is the application we want to place on our fog nodes or on the fog devices. Now for every application, we have some services. Those services could be like we have a patient monitoring system. We have a system to manage the beds in the hospital. We have a system to manage the pharmacy side of it. We have a system to manage the requirement in the hospital. So everything will be sensed by the sensors or the actuators because it is all based on the IoT part. So there are various services, and we would like to give the fog nodes to those services. So this is what we call as application placement. How we can give the required resources to our given application. I'm taking the example of smart healthcare. So let's suppose patient monitoring system is one of the service under this, or we have some sub services also which are under this. We would like to deploy them on the fog nodes. So what the application placement issue is? So let A be an IoT service oriented application with a set of QoS requirements. The quality of service is going to be the major factor in fog and cloud computing. So we need to manage the quality of service as well as we are deploying the application on the services on the fog nodes. So those QoS requirements are, let's suppose Q, and let's suppose F will be the set of the fog nodes. Now the question is how we are able to map each IoT service of A to some fog nodes into F after satisfying all QoS requirements set by Q and optimizing a set of objective functions O utilized to evaluate their quality. So all these things are in sync. We have this A, we have this F, we have this Q, and then we have the objective functions also. So this is a problem actually. To manage all these things in sync, this is the application placement issue. And moreover, the solutions could be many to many also. One IoT service could be deployed on multiple fog nodes, or multiple services could be deployed on multiple fog nodes. So this is going to be the application placement issue. This diagram will make the things more clear. So I have divided my application into set of services called S1, S2, S3, S4, and we can see here S1, S2, they are on the same fog server like this. Then we have this S3, we have S4, S5, S6. So this is many to many environment, and this is application placement as well at the same time. So the question is this only, the problem is this only, are we able to manage that? Are we able to do the things that I was discussing earlier? Are we able to do this mapping? This is the question. So from here we get the problem. Okay. Now, moreover, the application placement could happen at three levels: centralized, decentralized, and hierarchical. When we say centralized broker, it requires information from all the entities in the fog landscape, like fog devices or clients or clouds, to take the global optimization decisions. So centralized broker will take the decisions at global level, whereas the decentralized broker will take the information for only small number of elements or some elements only, not all, but some. So it is taking the local optimization. It is going for the local optimizations. Now the fix is, are we going for centralized or decentralized, or are we going with hierarchical one? Hierarchical one will be using the combination of both. But we have figured out from the state of the art there are some limitations of centralized broker. What is that? The first is, it cannot guarantee the efficient optimized solutions. You know, when we are giving the global optimizations, we are not considering what is the local requirements are. So global optimization solution is common for all. But are we taking care of every requirement? Are we taking care of all the QS requirements? No. So that has to be taken into consideration. So it is not going to guarantee the efficient optimized solution. Moreover, because it is global centralized manager, a single point of failure is going to be very dangerous for the entire system. It will be, for sure. Not only this, because we are sending the data from the fog nodes and IoT application to the centralized manager, we are also going to incur more network overhead. And later it is going to be problematic for us. And it is also limiting the scalability. We cannot go with enhancement of the system. Why? Because the centralized core is already taking a lot of responsibilities, and if we are going to add something more, it will be very difficult to manage. So these are some limitations that we are incurring in the centralized broker application placement work. So somehow decentralized application or decentralized broker has given us something like local optimizations. So we are doing the local optimizations for particular regions of fog nodes, and when we combine them together, we are taking care of every area. We are taking care of every aspects, and all QoS requirements are maintained, which is helping us. Moreover, the scalability could be there. We can easily add on the architecture, we can easily extend the fog landscape. Right? And this is another point. We talk about the communication overhead. Definitely, we have seen in case of centralized one, it is more as compared to the decentralized one. Now, talking about the hierarchical solutions are like semi-global. Semi-global means it is taking the global optimization as well, it is taking the local optimization as well. So the advantages and disadvantages of centralized and decentralized are coming in the form of hierarchical solutions. So again, this application placement is the open problem for the researchers. They can either go with making one centralized broker, they can go with the decentralized broker as well. But my recommendation could be people can go with the hierarchical solutions. That will be the novelty in this approach. Definitely. Very less papers I have seen on this, the hierarchical solution. So this is one aspect or one research advice I can give to the potential researchers on the application placement part. Now this is the summary of the state of the art which is done on the application placement, and primarily the techniques are divided into three: model based, search based, or framework based. People are making their own frameworks. They are not confined to the existing frameworks only. They are making their own frameworks, they are making their own methodologies, and they are working on that part. Some are using the search based techniques. When I say the search based, it comes to the heuristic or meta heuristic techniques. I hope everyone is aware of heuristic approaches. And the heuristic approaches, a very famous problem is their traveling salesman problem. Are we aware of this traveling salesman problem? I hope everyone is aware of. Then taboo search is there, which is very trending nowadays. Taboo search, even the swarm intelligence is also there. So swarm intelligence is something which will be covering the meta heuristic techniques as well. So heuristic techniques are going to give us a solution which is not the perfect one, but a good one, I would say. A good solution. But I will not say it is the perfect solution, right? And if I go with the meta heuristic techniques, there we are constantly improving the population using crossover and mutations. A classical example we can take of genetic algorithms. And what we generally do in genetic algorithm, we have the initial population, we do the selection, and then we do the crossover and mutation. Again, we do the selection, and until unless we are not coming to a perfect solution, I will not say perfect here also because it is not giving the perfect solution, but yes, the approximate solution is also coming in meta heuristic, but definitely it will be better one as compared to the heuristic approaches. So all the evolutionary algorithms will be comprising of this meta heuristic, and whatever resource management approaches I'm going to discuss, whether it is application placement or load balancing or task scheduling, more or less they are confined to heuristic or meta heuristic approaches more. Yes, they are also going with game theory, they are also going with some other approaches as well, but this is where they are more confined because they are going to find solutions after proper refinements. We have, yes, in heuristic, you can also cover the greedy approach. The greedy approach is there. Apart from that, backtracking or first or best fit strategies could also be covered under the search-based solutions. Then we have the model-based, and under model-based, we have ILP, integer linear programming or mixed integer linear programming. Or what is the role of these two? They are going to find a best candidate solution using a fitness function. So that fitness function will come in meta heuristic approach also, but this is going to be model-based solution will be using ILP and MALP for this, and not going with the population generation part, or I should say the mutation or crossover part. But yes, they are still using the fitness function. So these are the approaches that are used in the state of the art, and I can also generalize what is the network metric that is used, that is delay. Latency or delay is one of the most important factor that is covered under application placement issue. Now, the another area of concern is, are they covering energy consumption? Energy consumption has to be considered, but less stress is given on the energy consumption part as well. So this could be another novelty that we can go with. Now, the simulations that are taken into consideration, it is done with the help of iFoxing. This is the mostly used toolkit. And the final research advice on this, already I have given 2 or 3 research advices on this application placement approach. We can go with some more evolutionary algorithms, or we can also use the deep learning technique. Deep learning methods like convolution neural networks, VGG models, RNN models, we can use them as the data is big data, and we can work on that part. We can filter out the data, and even the game theory could also be used. So these are some more hot areas or hotspots you can work on. So this is the summary of application placement issue. Yes, I hope up to this point the things are okay. Yes, I'm audible to all audience.
Yes, yes, doctor, we can hear you.
Okay, okay. Now moving further with the next approach, that is resource scheduling. Resource scheduling could also be termed as task scheduling. Interchangeable terms. We can say task scheduling. Now I started with the application part. From application, we constructed services. Now from services, I can construct tasks. Let's suppose there are services S1, S2, S3. In every service, we have the set of tasks T1, T2, T3. So in the application placement part, we are able to deploy the services, but in the task scheduling or resource scheduling issue, we are going to manage the tasks which are available to us. So every service request could be divided into the set of tasks available. Now this problem, this task scheduling problem is NP hard problem. It is NP hard problem. When we study design and analysis of algorithms, we come across these NP hard problems. These are those problems for which the polynomial time solution is not possible. They are hard to crack because primarily these type of problems are multi-objective problems. We are not focusing on only one objective, rather we are working on multiple objectives. So maybe we are achieving one objective and the second one is not achieved. Second one is achieved or third one is not achieved. So managing all the objectives together will be a difficult problem. That is why it is coming under the NP-hard problem. So what the scheduling problem is? The problem is we have the set of tasks T1, T2, Tn. We have the set of fog nodes and we want to map them. At the same time, we would also like to manage the QoS requirements of the system. So this is going to be a tricky challenge for us, how we are able to manage the resource scheduling. And primarily the solutions could come via meta-heuristic algorithms only. Again, the meta-heuristic algorithms are coming because they work with evolutionary, they work with the swarm-based algorithms where we have brains of brains working. When I say swarm, it means the brains of brains are working. We have a flock of birds, how they fly. We have ants. We have ant colony algorithm, how they are going to work. Their brains are working together and they are giving us the best solution. They are not fixing on the local optimum, on the global optimum. They are working on the best possible solution. But still, that solution will be the approximate one. We don't say it is the best one, but yes, it is very much close to the best one. So meta-heuristic algorithms will play a very, very important role. Gray wolf optimization, whale optimization, they are very trending topics. Very trending. Self-swarm optimization, we can use them. Whale optimization, grasshopper optimization, we can use them. So this issue of resource scheduling is going to be a very tough challenge, but yes, doable, and there's a lot of research scope available into it. Moving further, this is the diagrammatic view that I was discussing. So whenever the scheduling comes, we know from operating system we have the waiting queue and the ready queue. In the waiting queue, the set of tasks are going to wait for their turn so that they can get the computational power or the processing power they are looking for. And from the ready queue, the jobs or the tasks will be picked up. So the scheduler that we are going to maintain here, the task of that scheduler will be to deploy those tasks on the dedicated fog nodes. Services we know, they are coming from the IoT applications, fine. But from those services, how those jobs, I can say jobs also, yeah, job schedule. Jobs or tasks are going to be deployed on various servers. So this is the resource scheduling issue. Now they also come in three terms like static, dynamic and hybrid. Scheduling problems generally comes with the arrival times. So when we come with the static scheduling approaches, the fog nodes are knowing about the tasks which are arriving to them. Their information is already known to us. So we know which fog node to give to a particular task. So the scheduling decisions are already known. That is why it is known as the static scheduling approach. Talking about the dynamic scheduling, here it is a surprise. We don't know about the nature of the task, about the arrival time, about the length of the task, about the MIPS, or whatever parameters which are associated. We are not aware of that. So that will be coming under the dynamic scheduling approaches. We are not aware of the things we are looking for. So again, this is going to be a very good problem formulation for us. We can make a problem into this. Are we able to make a dynamic scheduler for us for the tasks which are there coming from the IoT applications? So this is what we are looking for in dynamic scheduling. Then we have the hybrid scheduling approach, which is a mix of both static and dynamic. Very less work is done on the hybrid scheduling part as well. Primarily, if you cover the IoT applications, there will be a mix of tasks. Some tasks we are aware of and some tasks we are not aware of. Let's take an example. Again, I'm taking the healthcare example here. Or okay, let's move to another example. Let's take a smart city example. Healthcare examples I have already given for approaches. Now, in the smart city example, let's suppose we have a traffic controller area, red light traffic controller area. So constantly the data is coming and going and processing and going in the smart city. Fine. The data could be anything. Now, what could be the static scheduling here? The static scheduling is we have taken a consensus, we have taken an average that okay, at this particular time, this much of traffic flows. So we know that okay, this fog node can handle this much of data because on average we know at this particular time, let's suppose at 3 p.m. this much of traffic is going on, so that data could be handled by the set of fog nodes. So that could be the static scheduling. Now when the dynamic scheduling comes, let's suppose at 3 p.m. there was a major accident happened. So that is something which is a dynamic event happening. And fog nodes are not aware of this, that whether with that major accident what is going to happen. Maybe the traffic will increase, for sure the traffic will increase. So are we ready to handle that data? Are we ready to process that data? So that is a dynamic thing which is going to happen. Right? So this type of environment, are we able to ready? So if you are making a scheduler, your scheduler must be capable enough. It can handle the static things, it can handle the dynamic things as well. So now I'm coming to the summary of various approaches for resolving the resource scheduling issue. It comes to the heuristic algorithms only. Because it is multi-objective problem and heuristic algorithms are helping us into this part. And they are also working on two parts, minimizing the latency and the response time. These are the two performance parameters the state of the art is looking for. And they are also increasing the dynamic efficiency of the system. Two toolkits or two implementation strategies they are working on, like they are using MATLAB and iFoxim toolkits to evaluate their algorithms or their work. What research advice we can offer here on the research scheduling issue? One I have already given. Try to either implement the dynamic scheduler or the hybrid scheduler. This is one advice I can give. And the other one is you should go for such systems where the scalability issue is also taken care. We should also go for the self-adaptive resource scheduling. This is another issue. Like when the resources are less or when the resources are more, are we able to handle them at the same time? So that self-adaptation is also the another research issue that we can look for. So two approaches are done and 4 to 5 research problems we have seen from there. The next is the task offloading. And this is very much different from the task scheduling part. Offloading will come when the tasks are scheduled. Once the tasks are scheduled, or maybe the tasks are given to such a fog node that is not able to handle it. Or maybe you are processing the task at the edge layer only, and at the edge layer we have the mobile devices also, and mobile devices are not that much competent, they can handle or process the task. So are we able to offload the task? Offloading means migrating the task from one device to another, from one node to another. Are we able to do that? Or we can say, are we able to transfer the compute intensive task from the resource limited IoT devices to the resource rich computing nodes? So this offloading will come once you have scheduled everything. So one could be the offloading source from where the task will be transferred, and one will be the offloading destination where the task will come. So are you able to design an efficient task offloading approach? And what type of applications we are covering here? Like augmented reality, virtual reality, face recognition, multimedia delivery, gamification, and so on. There are so many applications which are resource intensive applications. Are we able to transfer them? Are we able to offload them? This is what we are looking for. Now, where the problem could come? The problem could come, we have such devices which are not having sufficient computational power, we are not having sufficient battery energy or the storage space. And they generally could be seen in mobile devices, and mobile devices work at the edge layer. The same layer where the IoT devices are deployed. So are we able to transport our task onto the layer or onto those devices which are resource rich? This is what we are looking for. This is task offloading. Diagram will make the things more clear, as we can see here. So there is one offloading manager which is going to handle two things here: VM migration, virtual machine migration. Virtual machine migration could happen, or the offloading. This is the offloading scene which is happening. So from here, from the fog gateway, from the IoT device layer, the offloading will start. Offloading manager will take the decision where to offload the task. Obviously, the task will be offloaded in the fog tier itself. So in the fog tier, the task will be offloaded, and once the processing is done, the result will be returned back to the offloading manager, and then the result is coming back to the IoT application. So this is the flow graph that we can understand here. Okay, so from the gateway is coming to the offloading manager. Offloading manager is now moving that task to the freely available resource. Computation will happen. Result will be returned back to the same IoT application which was looking for processing. Now the question is, are we able to code this offloading manager well? Are we able to track the fog regions or the fog nodes where the sufficient fog nodes are available for offloading? Are we able to map the requirements we are looking for? Because maybe the task requirements are more and we are not having that fog node available. So what is the task of offloading manager here? Are we able to find such fog node? This is a very simple environment that I am depicting, but in reality, the fog test bed will be, very complex. There are so many devices which are working in tandem. But are we able to manage them? Are we able to find the sufficient fog node or fog device for the offloaded task? This is what we are looking for in task offloading issue. Under this, again, we have two categories, single and multiple. In single type offloading approach, computational tasks can be offloaded to only one fog. Whereas in multiple type offloading, there are more than one destinations to offload the computational task. So this is what the problem area could be. This is another research advice I can give here in the task offloading. Are you able to formulate such approach in which the multiple type offloading is possible? Are we able to detect multiple fog nodes for the parallel processing to meet the quality of service? See, in case of task offloading, latency is going to be a very major factor. The reason is simple. Initially, we took the time to find a particular device to process our task. Let's suppose that device was at the edge layer. This was device 1. And after nanoseconds, after fraction of seconds, we found that this device is not competent enough to handle the task. Then what? We will waste another time to approach the offloading manager. It will take again some time to search for a particular fog node. So double time taken for finding. This is T1, this is T2, this is the task actually. So this will be double time taken. Okay, T1 time we cannot control, but can we control this T2 factor? The total time, because the total time T is given by T1 plus T2, where T1 time is okay, accidentally we found something which is not able to handle, but are we able to control this factor? This is what the research area could be, right? So when you look for multiple type of loading approaches, are we able to find something where less time is taken? Or you have multiple destinations, fine. Which one is the best? This is the task we can do. So we have two categories of task offloading. Now coming to the summary part, again, heuristic-based techniques are used. Queuing theory is used because the ready queue or the job queues are maintained. Game theory is used. There is one Lyapunov optimization. This is again one type of optimization used. And the applications I already discussed: virtual reality, face recognition, augmented reality, gaming, gamification, and so. And they have worked on the energy consumption part, energy consumption metric, but latency is another factor that is required to be taken care. They have used MATLAB tool for evaluating the performance because mobile applications are also involved into it. This is more of edge computing approach. Resource are found on the fog layer, but I would say the task of loading would be implemented as edge computing part, more or less it will be, because we are only taking the support of fog computing for substituting the things, but at the end of the day we are returning back the result to the edge layer only. So what is the research advice into it? One or two I have already given. This is another point of view from the state of the art. That is, are we able to find or determine the right amount of resources required? Are we able to achieve scalability of mobile applications? This is again a very important task because mobile applications are resource constrained. Or security and privacy of data. Why? Security and privacy we are saying here because we are offloading to some other device. Maybe initially when we found something to process over data, that was found because that was at the local place. But when we are looking for something in the fog layer, then the security and the privacy issues are going to come for sure. So three approaches are now successfully done, and these are the research advices on which the research scholars could work in the task of loading part. Now the next thing is load balancing. Now this is again very important. Load balancing in cloud is very trending topic. If I say 3 to 4 years before, it was very trending topic, and even today also it is. So now we are to the load balancing issue. Tasks are scheduled, even tasks are getting offloaded also. But there could be a chance we are not taking care about the loads on the fog nodes. Let's suppose we have fog nodes F1, F2, F3, F4, F5, and so on. And the loads are not balanced. Their loads are not balanced at all. We are keep on offloading the task, we are keep on scheduling the task, but are we taking care of whether F1 is overloaded or underloaded? F2 is overloaded or underloaded? We should take care of that also. So that is a very important thing. It comes under load balancing issue. So when we are able to manage the incoming workload, are we able to manage the incoming workload in terms of what? In terms of judicious load allotment. We should judicially allocate the load. So we should find the strategy to avoid the underload or overload of the fog nodes. And what will happen with this? Consequently, the response time will be minimized and the throughput will be increased. For sure, it will be. So we need to find something where we have the minimum response time so that we can implement scalability. We can also avoid the bottlenecks. Now, bottlenecks are going to come when we are improving something. The other thing is automatically, disturbed. So that thing we need to manage in the load balancing issue. So there are some more challenges like high network latency for sure. When the load is not balanced, we are waiting for the response from one node, and let's suppose that node is overloaded already. So definitely it will take more time. It will take more time to give us the result back, and that could be troublesome for us. So we need to manage that. And fog nodes are also considered to be the local cloud servers, and because of their heterogeneity and dynamism, load balancing strategies need to be applied. They are not similar as of cloud computing. Cloud computing load balancing is different concept because they have the centralized approach, they have the data centers, we know everything about all the configurations. But here, sometimes the fog nodes are mobile, they are keep on changing, so we need to manage the loads on different fog nodes. So this heterogeneity and dynamism of fog node is sometimes a big problem, and we need to manage the loads accordingly. So our task will be to design a load balancer which is taking care of everything, because the scheduling is happening at the same time, application placement is also happening at the same time, offloading is going on. So when these three activities are going in parallel or maybe one after the other, are we able to design a load balancer which can take care about these things? Or maybe the consequences are also handled at the same time? So this is what the task would be for the potential researchers. Are you able to maintain or make such load balancer? So this is what this diagram is depicting to us. So when all the three approaches are working in tandem, are we able to maintain the balancing of the load at the same time? This is what we are looking for in load balancing issue. Now, if I come with the various approaches of load balancing, they could be happening at the centralized level, decentralized level, or hybrid level. When it comes to the centralized load balancer, it is having a global controller. That global controller will have the entire knowledge of the available fog resources and the IoT demands. So there is a single point of control. And when the number of fog nodes are increasing, the single point of control may incur a lot of overhead. There will be a lot of overhead. And how we can manage this? This is a trickier challenge. In the decentralized solutions, we have various brackets, or we have various controllers available which are managing their own fog areas. This is fog area 1, this is fog area 2, this is fog area 3, and every controller is responsible for only its own area, unlike the centralized load balancer. So this is the decentralized approach. And in the hybrid solution, it could be we have a common point for every fog area, but for all the fog areas, we have a centralized one also. This is what we call as the hybrid solution. Are we understanding this? We have a central point for every fog area. In every fog area, we have various fog nodes available. And for every fog node, we have the central point, the central load balancer here. And when we collect all the fog areas together, we get the centralized one. So again, one research advice I would like to give here: go for the hybrid solutions. That is the best fit. And very less work is being done on this part. So far, centralized load balancers or maybe decentralized solutions are given, but very less work is done on the hybrid solution part. So some have used graph theory, some have used differential algorithms or linear programming or parallel Othello groups methods. This is something unique method which was created, but more or less they are working on the centralized or decentralized part only, but they're not working on the hybrid part. So with more meta-heuristic algorithms or hybrid techniques, you can come up with the solutions of hybrid methods as well, hybrid load balancing approaches as well. And they have evaluated latency and response time as the performance metric. And another research advice, energy consumption. It has to be taken into consideration. Nowadays, energy is a very important factor. Energy consumption must be taken into consideration. And for the simulation environment, most of them are going with the cloud sim approach. So what is the research advice into this? The first is we need to go with the hybrid load balancing techniques that I already told you. Why? Because we have the dynamic and heterogeneous fog networks. Scalability, again I always say the scalability issue because it is not managed under all the approaches. And we should also focus on the fault tolerance approach. This is very important. We have fog nodes, let's suppose. The loads are distributed onto them, but we don't know, let's suppose at one time one fog node is faulty. It is not working, it is failed. Then what will happen? We are waiting for a response from this fog node, but that response is not going to come. This is one aspect. The other aspect is, let's suppose some more load is coming and now load balancer has recognized F1 is already failed. Then what will happen? The load will be more on F2, F3, F4 and F5 because now they are taking care of everything. They are taking care of the incoming load also, or maybe load balancer after some time has recognized F1 is failed, so that load will also be shifted on these nodes. Consequently, what will happen? Response time will be more. So you should design such a load balancer which is able to manage the, or which is able to detect the fault. This is another research advice I can give in this part, in the load balancing issue. Now the next part is resource allocation. Now this is going to be a generic sort of issue, resource allocation. But the major thing is, in resource allocation issue, we are not only talking about IoT and fog. We are also talking about here cloud. This is the big difference with the other approaches when it comes to resource allocation. Now this line is very important. The resource allocation problem in fog computing is formulated as a double matching problem. This is what the major thing here is. Again, it is NP hard problem for sure, but it is a double matching problem. Why? We are looking for cloud servers and fog nodes are coupled for IoT users, while fog nodes and IoT users are coupled for cloud servers. So here we are in hunt of cloud servers as well when we are going with resource allocation. Yes, earlier we were hunting for only fog nodes, but now we are looking for cloud servers as well at the same time. So are we able to map that? Are we able to couple it? This is what the double matching problem comes under resource allocation. So the objective is what? To find the optimal cloud server, fog node and the user pair for total IoT users to achieve the objectives. And what is that objective? Maximize the QoS and minimize the cost. So this double matching problem is taken into consideration here in the resource allocation part. And again, I already told it is going to be NP hard problem, and who is going to help us here? Meta heuristic approaches again, or the evolutionary algorithms will help us. So this is a diagrammatic view. I already told about this, and again it is many to many problem. Many to many problem here. The cloud layer will also come into picture. Are we able to couple it with the cloud servers as well at the same time? This is what we are looking for in resource allocation issue in fog computing. Now the next thing is, what are the various categories of resource allocation? Under this we have auction based and optimization based. Now, when I say auction based, it is very much similar to that business type of thing where we have a market based pricing approach, where we have the bidders for the fog nodes, or the best bidder is going to get the fog node. So we can think like this. This is just a simulation type of thing we are doing here, but actually it is called as auction based approach, or I should say the market based pricing. The next is the optimization based, where again we are looking to manage the double matching problem, or we are looking to go for local and global optimizations at the same time. So are we able to find the cloud servers or the fog nodes for the IoT users? This is what the resource allocation problem is looking for. Now, if I go with a summary of various approaches for resolving the resource allocation issue, here we can say the Patry nets, approximation algorithms, game theory, they are used to enhance or to give us the efficiency we are looking for. And we are working on the real-time applications like vehicular network applications or video streaming applications when it comes to the resource allocation issue. And most of the work are working on iFog Sim simulator again, and the performance metrics are delay and latency. They are same. Should be or. By mistake, and is written or. More applications I would like to mention: healthcare applications or mobile blockchain and Internet of vehicle transportation applications are also considered in the resource allocation issue. Last but not the least, the resource management approaches will be resource provisioning. Provisioning means you are deciding, okay, these number of resources are required. You are already freezing the resources. That is the provisioning part. Now, provisioning can happen in two ways: over provisioning or under provisioning. In the over provisioning, we are allocating the resources for the given IoT services more than the actual requirement. And what will happen with this? You are giving unnecessary cost. This is unnecessary. Why to waste all more fog nodes if you require less? So this is over provisioning problem. So we should design the methods which could help us to provision the resources. And then we have the under provisioning also. And under provisioning means we are violating, or we are going with SLA violations. SLA stands for service level agreements. When it comes to cloud and fog computing, SLA is going to play a very important role. Those agreements are required to be managed. So under provisioning means what? You are deciding, okay, these number of resources are required, but actually require more. So at that time, what you are doing? You are violating the SLA. And again, it will be a loss to the IoT users. So resource provisioning is again a very tricky challenge, because definitely we need to fix some resources. We need to buy some resources. We need to fix some resources. And because IoT environment is highly dynamic, fluctuations will happen for sure. Load will change, fluctuations will happen, and with this, over provisioning and under provisioning is bound to happen. So are we able to manage it? This is what the problem is: resource provisioning. So we can see here there are resources for computation, storage, memory, bandwidth. All the pool of resources are there. There is a resource provisioning manager. So your task will be to code this. Are we able to code the resource provisioning manager so that we can handle the over provisioning and under provisioning? See, we cannot nullify it, but still, are we able to minimize it? This is what we are looking: over provisioning and under provisioning. So again, three very interesting types are available in the resource provisioning. It will be reactive, proactive, and hybrid approaches. Under reactive policy, you are not going to perform any prediction. You just respond to the current system status. So what the status is? the resource provisioning manager will see, and accordingly the resources are provisioned, they are allocated. Fine. So here we are not applying any intelligence. We are not doing any predictive analysis that in future how many resources more will be required or how many resources less will be required. We are not focusing on that part. So this is coming under the reactive policy. And what is proactive policy? We are predicting the things. Okay, in future there could be a chance that the number of resources will be required more, so we are going with the buffer already. But this is not going to be true every time. Maybe we are going with a buffer, but let's suppose you don't require that resources. Because predictions are always not true, na? They're going to be 50-50 part of it. But yes, reactive policies are very static type of thing, but proactive policy can help us. They can reduce some sort of over and under provisioning. Because we are already prepared with what is going to happen, and how we can prepare us via time series analysis, or maybe the neural network based, or some machine learning techniques we can apply on the existing trends to determine or to perform some predictions. But again, we have a mix of these two, reactive and proactive policies. That is the hybrid policy. So hybrid policy is going to use the scaling out approach as well as the scaling in approach. When we say scaling out, provisioning a new fog node, scaling in, releasing a fog node. So it will be a mix of both. And this is another research advice I can give. Reactive policies are very easily implementable, or we can implement them. There will be no problem. Proactive policies will require intense machine learning algorithms and the prediction power that we can use, or the time series analysis as well. But we can come up with something which is known as hybrid policy, where both are used. So it can definitely reduce the amount of loss that is going to happen with reactive or proactive. This is another research area we can work on. So coming up with a summary of various approaches which are developed over the years. Again, heuristic based techniques are used. And talking about the performance metric, they are not considering all performance metrics in one case study or in one work. Some works are going with latency, some are going with cost, some are going with throughput, CPU utilization, some are going with energy consumption, but they all are not taking all parameters in the same work. So this could be another research challenge. Are we able to manage all the performance metrics at the same time when it comes to resource provisioning part? This could be another problem formulation we can go with. And most of the works are working on the smart city applications. We can consider some more. We can go with industrial IoT as well, because in the industrial IoT part also, resource provisioning will play a very important role, because everything is smartly done. Smart devices are involved in the industry part, and if you are able to make such policy where you can provision the resources, you are going to give a good benefit to the IoT users in the IIoT part. Coming up with various toolkits or various implementations which are being done, it will be JMT, MATLAB, Apache JMeter, CloudSim, and iFoxing toolkits to validate the solution. This is done in the state of the art. New researchers can go with some other implementation toolkits as well. So these were the various resource management approaches which are developed over the years, and I hope up to this point the things are okay. I'm up to the conclusion part of this workshop. Now, what are the main challenges of resource management in fog computing? So this is not only confined to the resource management part. These could be some open issues or challenges as well, like Privacy and security. This is something that I have not discussed in the discussion. I have not gone with this privacy and security. So one another topic that I can give, it could be implementation of blockchain. Are we able to apply blockchain in the fog computing environment to enhance the privacy and security? So this could help us. Or we can combine this blockchain with IIoT. Or we can also go with IOV. We can also go with uh, smart cities. Yes. So you can apply the blockchain to achieve the privacy and security. So this could be a separate topic altogether. Then the scheduling directions, scalability and mobility. Scalability issue I always highlighted when I was discussing. Offloading direction, interoperability. Are we able to operate successfully with the fog nodes? Energy consumption is the another area. Energy consumption factors are very less stressed upon in the state of the art. So we can also take this factor into consideration to make our problem. So this is what my discussion was all about, and I hope uh, the students or the research scholars or the potential researchers or respected professors are able to get what I was trying to say, what my intention was. Thank you. Any queries?
Thank you very much, sir. And Aisha, so please feel free to let me clear this very frankly. Please feel free to ask any kind of question you have in your mind and anything related to the topics, or you want some additional details related to it. And even after the workshop, when you're starting studying these topics and you have any queries, we have the email addresses over there for the ERIC team. So you can email to the contact details and we'll get back to you with all the concepts and any help in implementations, problem solutions, whatever kind of help you need, we are happy to help you. Yeah, now please feel free to ask the questions.
Thank you, Dr. Aman. Thank you, Dr. Salid. That was a very informative session. I enjoyed it from the beginning, and I think the attendants sure they have questions and interest in all the research questions Dr. Salil mentioned, and encourage the participant here in the session 14 to, if they have any questions, they can write it in the chat or they can ask through the mic.
Thank you so much, Ms. Aisha, for hosting this session. And I would like to say thanks to Dr. Raman Singh and Dr. Sari for their time, for this amazing session, and for their support to IDLab by bringing this very hottest topic of research to the audience, which I do believe will be really beneficial for all of them and definitely for us. We are looking forward to the second session, which will be mainly hands-on. So thanks again for your time and for your support.
Thank you very much, Dr. Sawa. Let me admit this to all the faculties. A big thanks to Dr. Saba for giving this opportunity to all of us and for this interaction. And it was all her initiative. And great thanks to her. Yeah, thank you very much.
Thank you, Dr. Tanzia. Thank you very much. You are well known for this helping communities and spreading the knowledge. Thank you, Doctor.
We are thankful to all the audience as well for attending this session. Thank you so much.